To determine the correct size of service conductors for a panel, especially over long distances, several factors need to be considered, with the National Electrical Code, or NEC, serving as the primary guide. Article 310 of the NEC provides essential information on conductors for general wiring. The first step is to determine the total load that the conductors will carry. This involves calculating the sum of all the loads connected to the panel. In the case of a 400 amp panel, you need to consider any potential future load growth. To account for this, you can multiply the total amperage of the largest load by a factor of 1.25, also known as the panel factor. So 400 amps multiplied by 1.25 equals 500 amps. This 500 amp value will be used to determine the minimum ampacity that the service conductors must be rated for. Secondly, adjusting for voltage drop is crucial, especially over long distances. Voltage drop occurs due to the resistance of the conductors, causing a reduction in voltage at the load end. Excessive voltage drop can lead to equipment malfunction or damage. For irrigation pivots, a maximum voltage drop of 5% is typically allowed. The formula to calculate voltage drop percentage is voltage drop percentage equals 2 multiplied by the line length multiplied by the load in amps, divided by the conductor resistance multiplied by the conductor cross-sectional area. Line length refers to the one-way distance between the source and the load. Conductor resistance is typically given in ohms per 1000 feet, and conductor cross-sectional area is measured in circular mils. Using this formula, you can determine the voltage drop for a given conductor size and load. Thirdly, to choose the appropriate conductor size, refer to Table 310.16 or Table 310.18 in the NEC. These tables provide ampacity ratings for various conductor sizes and insulation types at different temperature ratings. Select a conductor size that meets both the ampacity requirement, as determined in Step 1, and the voltage drop requirement, as calculated in Step 2. Keep in mind that the ampacity of a conductor is affected by its insulation type and the ambient temperature in which it is installed. Be sure to use the correct ampacity adjustment factors as specified in the NEC. Fourthly, once you've selected a conductor size, it's essential to verify that its ampacity is sufficient for the total load current. The selected conductor must be rated to handle the 500 amps calculated initially, considering the panel factor. In the specific case of a 1500 foot distance and a 400 amp load, an example calculation can be performed to illustrate the process. Using Table 310.16 for 0% to 2% voltage drop with 75 degrees Celsius conductors, a 350 kc mil aluminum conductor is examined for suitability. A 350 kc mil aluminum conductor has an area of 350,000 circular mils and a resistance of 0.169 ohms per 1000 feet. Plugging these values into the voltage drop formula, voltage drop percentage equals 2 multiplied by 1500 feet multiplied by 400 amps divided by 0.169 ohms per 1000 feet multiplied by 350,000 circular mils, which equals 3.33%. Since this value is within the acceptable 5% limit, the 350 kc mil aluminum conductor appears to be a viable option. Now, it's important to verify the ampacity of the 350 kc mil aluminum conductor. According to Table 310.16, a 350 kc mil aluminum conductor is rated for 465 amps. However, because the total load current is 500 amps including the panel factor, a 350 kc mil aluminum conductor is not adequate. In this case, you would need to select a larger conductor size with a higher ampacity rating. A 500 kc mil aluminum conductor, for instance, has an ampacity of 560 amps, which exceeds the total load current of 500 amps. Plugging the values for the 500 kc mil aluminum conductor into the voltage drop formula, voltage drop percentage equals 2 multiplied by 1500 feet multiplied by 400 amps divided by 0.126 ohms per 1000 feet multiplied by 500,000 circular mils, which equals 2.86%. This value is within the acceptable 5% limit, so the 500 kc mil aluminum conductor would be appropriate. Several key considerations must be emphasized. Firstly, the panel factor of 1.25 is used to account for future load growth. It's a common practice to oversize the service conductors slightly to accommodate any potential increase in load. Secondly, the conductor length in the voltage drop formula is multiplied by 2, since voltage drop is calculated for the total round-trip distance of the circuit. Thirdly, other factors, such as temperature, can affect voltage drop calculations. Higher temperatures increase the resistance of conductors, leading to greater voltage drop. Therefore, it's essential to consider the ambient temperature in which the conductors will be installed and apply any necessary correction factors. It is also important to consider the type of termination at each end of the conductor. Terminations are typically rated for 60 degrees Celsius, 75 degrees Celsius, or 90 degrees Celsius. The lowest temperature rating of any termination in the circuit will determine the maximum ampacity of the conductor. In addition, the NEC specifies requirements for conductor insulation. The insulation must be suitable for the voltage, temperature, and environmental conditions in which it will be used. Common insulation types include THHN, THHW, and XHHW. Each type has its own specific properties and limitations. It is crucial to consult the NEC for detailed information on insulation requirements. Grounding and bonding are also essential aspects of service conductor sizing. The grounding conductor provides a path for fault current to return to the source, helping to protect against electrical shock hazards. The bonding conductor ensures that all metal parts of the electrical system are at the same potential, reducing the risk of electric shock. The size of the grounding and bonding conductors is determined by the size of the service entrance conductors. Refer to NEC Table 250.122 for guidance on grounding conductor sizing and NEC Section 250.102 for bonding conductor sizing. Furthermore, the NEC provides guidelines on the installation of service conductors. The conductors must be protected from physical damage and installed in accordance with the NEC requirements for raceways, cable trays, or other approved methods. The conductors must also be properly supported and secured to prevent strain on the terminations. The NEC also addresses the issue of conductor dirting. Conductor dirting is required when multiple conductors are bundled together in a raceway or cable. The heat generated by the conductors can raise the temperature within the raceway, reducing the ampacity of the conductors. NEC Table 310.15 provides dirting factors for various numbers of conductors in a raceway or cable. In addition to the NEC, local codes and regulations may also apply to service conductor sizing. It is essential to consult with the local authorities to ensure that the installation complies with all applicable requirements. Selecting the appropriate overcurrent protection device, such as a circuit breaker or fuse, is also a critical part of service conductor sizing. The overcurrent protection device must be sized to protect the conductors from overload and short-circuit conditions. The NEC provides guidelines on the selection of overcurrent protection devices in Article 240. The overcurrent protection device should have an ampacity rating that is no greater than the ampacity of the conductors it protects. It is also important to consider the interrupting rating of the overcurrent protection device. The interrupting rating is the maximum fault current that the device can safely interrupt. The interrupting rating must be sufficient for the available fault current at the point of installation. In some cases, it may be necessary to use current-limiting overcurrent protection devices to reduce the magnitude of fault currents. Current-limiting devices can help to protect equipment from damage caused by high fault currents. The NEC also addresses the issue of voltage drop in branch circuits. Branch circuits are the circuits that supply power to individual loads such as lighting fixtures, receptacles, and appliances. The NEC recommends that the voltage drop in branch circuits should not exceed 3%. Excessive voltage drop in branch circuits can cause equipment to malfunction or operate inefficiently. To minimize voltage drop in branch circuits, it is important to use the correct conductor size and to keep the circuit length as short as possible. In addition to the factors already discussed, there are a few other considerations to keep in mind when sizing service conductors. Firstly, consider the type of load being served. Some loads, such as motors and transformers, have high inrush currents when they are first energized. The service conductors must be sized to handle these inrush currents without experiencing excessive voltage drop. Secondly, consider the power factor of the load. Loads with low power factors draw more current than loads with high power factors. The service conductors must be sized to handle the increased current demand of low power factor loads. Thirdly, consider the harmonic content of the load. Some loads, such as electronic devices and variable frequency drives, generate harmonic currents. Harmonic currents can cause overheating of conductors and equipment. The service conductors must be sized to handle the increased heating caused by harmonic current. In summary, sizing service conductors for a long-distance panel feed requires careful consideration of several factors, including the total load, voltage drop, ampacity, conductor type, insulation, grounding, bonding, overcurrent protection, and local codes. By following the guidelines in the NEC and consulting with qualified electrical professionals, you can ensure that the service conductors are properly sized and installed, providing a safe and reliable electrical system. Remember to always prioritize safety when working with electricity. Energize the circuit before working on any electrical equipment and follow all applicable safety precautions. If you are not comfortable working with electricity, consult with a qualified electrician. And always consult the latest version of the NEC, as codes and regulations can change over time. Keeping up to date with the latest requirements is essential for ensuring a safe and compliant electrical installation.